Hi guys, welcome to another episode of MrLopezClasses.com. This is the chapter A of our Marine Corrosion book. In this chapter we are going to continue with the corrosion in the hull. How the hull is affected for corrosion. Yes, it's possible affect the hull if you select a proper hardware, if you select a proper sacrificial anodes, you can affect the hull. For that reason, in this chapter, we are going to study those parameters and how can I protect my boat, how can I protect the hull of my boat with good sacrificial anodes, with proper fittings, with proper through hulls, with proper hardware, and with proper coating. What paint is appropriate for the bottom of my boat, what paint is not appropriate. This is the analysis that we are going to do in this chapter. And we are going to advance step by step in order to understand what happened with the hull, what happened in between the hull and the water, and what type of corrosion can be created in that binder, and what type of corrosion can be created in between the hull and the water. In the hull, normally we have two types of corrosion. Corrosion by erosion, that's the most common, and the electromechanical reaction in between the water, the hull, and the hardware in the hull. Erosion in the hull, yes, depend of the water, depend of the amount of sand in the water, my boat will be eroded by friction, by mechanical friction. Yes, the sand dispersed on the water work like a sandpaper and eroded the boat and attack the boat. For that reason, we are going to be concentrated in the concentration of sand, the temperature of the water, the salinity or the alkalinity of the water. Depending on those factors, we are going to select the appropriate sacrificial anodes and the hardware. Erosion on the hull is basically mechanical from corrosion and is produced by friction. This can be mechanical corrosion. For example, sandy water flowing around the hull work exactly like a sandpaper, yeah, and eroded the boat. Look at those areas, completely eroded for mechanical friction in between the water and the surface of the hull. High speed flow corrosion. What is the meaning of that? It's another type of corrosion. It's produced for the high speed of the flow. And at the end is pitting corrosion. You remember pitting is like small drills that perforate the surface, and it's very common in the rudders. Look at this rudder in this particular example. It's completely eroded, but it's basically pitting corrosion. It's a lot of bubbles that explode against the blade of the rudder. Similar to decapitation, pretty similar, and produce that pitting corrosion in different areas. You see those holes of material eroded. This is basically because if we cut it, the rudder is, you remember, it's like this, and this is the leading edge. This is the leading edge. If you have dents over there, when the flow of water is coming, the flow produces turbulence, and the turbulence produces bubbles, and the bubbles explode. This is basically because on the leading edge of the rudder, there are cracks, there are dents, and those dents, when the water enter, produce bubbles, produce turbulence, and those turbulence produce a lot of bubbles, and the bubbles explode against the face of the rudder and eroded the rudder. That rudder is completely eroded. This is a good example of erosion produced for flow corrosion. Is the highest speed of the water produce friction in between the surface of the material and the water, the liquid. Okay, how can we avoid that? With a good service. Good service on the blades of the propeller, good service on the rudder. How can you avoid that situation? Is with good service in the bottom of the boat. Cleaning the propellers, cleaning the rudders, paint with the appropriate coating material, and protect those surfaces, especially the rudders and the propellers, and verify that those surface doesn't have cracks, doesn't have bends, in order to avoid the creation of bubbles around the surface. Electrochemical corrosion is the corrosion that we know until this point. It's when you have two dissimilar metals together, the more noble metal attack the less noble. Don't forget, what is the meaning of more noble? We are going to refresh our table of electronegativities. You remember? It's the amount of energy of each element. There are elements with more energy, with more electronegativity. They are located in this area. And there are elements with less electronegativity located in this area. Yeah, depending on the electronegativity, there are elements more nobles with high electronegativity or less noble. Remember that the elements with higher electronegativity are fluorine with 4.0, oxygen with 3.5, this is millivolts, chlorine with 3.0, and elements with low electronegativity, rubidium, cesium, francium, with 0.7, 0.8, 0.9 millivolts. Depending on the level of energy, depending on the electronegativity, the element is considered more noble or less noble. In general, the more noble metal attack the less noble, and the less noble release electrons and be corroded. Okay? For that reason, you say, I am going to protect the metals in my boat with a less noble material. The oxygen attacks the less noble, and the more noble metal is protected. Examples: the chaff. The chaff is protected with pieces of zinc, like this, and the oxygen attacks the pieces of zinc, and the chaff stays in good conditions. The propeller, exactly the same. The zinc at the end of the propeller is attacked. The oxygen attacks the zinc, and the propeller is protected. The propeller in that case is more cathodic, and the anode at the end of the propeller is more anodic. It's the sacrificial anode because it's less noble. That's clear? The less noble metal will be eroded. The less noble metal is the donor of electrons. The more noble is the cathode, absorb electrons. This is the situation. This is important that you keep clear that concept, because in this chapter we are going to play with that concept, the concept of more noble or less noble. More anodic is less noble, release electrons. More cathodic is more noble, absorb electrons. Okay? With that concept, we are going to understand later how is the process to select appropriate the sacrificial anodes according with the material of the hull and the type of water. Equal electronegativities. This is another important concept. Equal electronegativities, equal level of energies. If you check once again in the periodic table, there are elements with similar level of energy. For example, we are going to check copper. Copper is 1.9 and iron is 1.8. You remember the steel alloys? There are alloys based on iron. There are steel alloys, stainless steel is an example. There are steel alloys with a 1.9. The level of energy is 1.9. It's basically the same like the copper. Copper is 1.9. Yes, for that reason, you found it that there are a lot of steels, a lot of iron alloys that can be welded with the copper rods, because the level of energy is pretty similar, and also the structure. This is topic of other course, the course of materials for engineers. According with the structure, BCC or CDC, if the structure is similar and the level of energy is pretty similar, you can weld that different material with the other different electrode. Yes, for example, there are a lot of steel alloys that can be welded with copper rods. Yes, with oxyacetylene. You remember some years ago, it's common that you can weld some iron alloys with copper rods, because the level of energy of both materials is pretty similar. This is very, very important. In the opposite way, when you have the similar levels of energy, is where one metal corroded the other one faster. And the best example in marine application is copper and aluminum. Copper, if you check the periodic table, copper is 1.9 and aluminum is 1.5. It's a big difference. For that reason, copper and aluminum, and additionally the structures, are completely different. Completely different. Those metals, those alloys, are not good in marine environments. For that reason, you need to be careful when you have a boat with an aluminum hull with the hardware used in that boat. Of course, the true hulls in bronze, no, because the boat is in aluminum. Probably you need true hulls in stainless steel, marine grade. Stainless steel is a good choice for true hulls and hardware for aluminum boats. This is critical. This is important. When you have a boat in aluminum, with an aluminum hull, you need to be careful with the screws, with the washers. Never use screws, never use washers based on copper. Nothing. Be careful if somebody drops a penny in the bilge of your aluminum boat. That penny goes into the bilge. If you have humidity in the bilge, you have copper, aluminum, and salt water. The copper attack the aluminum and produce a hole, and you can sink the boat. Be careful with that. If you have an aluminum boat, you need to check the bilge periodically for pennies, for washers, for balls, for screws in copper. For fittings, the people drop fittings, copper fittings, into the bilge. That fitting destroyed the aluminum. That's important. We are going to talk later about that. With aluminum hulls, you need to be careful with a lot of topics. The hardware is one of the topics. The other one is the bonding. Never use the structure of the hull, the aluminum hull, like the ground of my boat. The hull is not the ground. You need to create a separate ground, properly isolated. Yeah. Okay, the electromechanical process. Don't forget that the difference between galvanism and electrolysis. Galvanic corrosion is when you have two dissimilar metals together in a marine environment. That's it. Only with the difference of energy in between both metals is enough to produce a small arc of electricity, and that small arc of electricity is enough to destroy the less noble metal. The more noble metal attack the less noble, and the less noble will be eroded. This is galvanic corrosion. Electrolysis is galvanic corrosion plus extra current in between both of them. Yeah, when you have a cable, positive cable in the harness of the engine touching the metal, that positive cable touching the metal accelerate the corrosion in between dissimilar metals, in this particular case in the block of the engine. Okay? In other words, electrolysis is galvanic corrosion plus current. Normally is DC current, a small DC current. Yeah? For that reason, check the leaks. You remember the previous episode when I explained the procedure with the amps method or with the volts method to check where are the leaks. Okay, and now we are going to try to understand how the electrodes works and why some electrodes are better in some conditions and why some electrons are better in this type of hole and why some sacrificial anodes are better in some conditions and not good in other conditions, and in what case are recommended this type of sacrificial anode or the other one. We are going to check exactly in each situation what is the sacrificial anode recommended. How does the zinc anodes work? Basically, it's because the zinc releases electrons. Because zinc in comparison with the other ones is less noble and protect the other metals. For example, zinc in comparison with copper alloys for propellers or for rudders, the zinc is good because the oxygen attacks the zinc and the copper alloy, the nibral, will be protected. And that's it. This is basically the explanation. The zinc will emit current that rise and equalize the electrical potential. Right now I am going to explain what is the meaning of that electrical potential. You remember that at the beginning of our course of electricity, when we explain the batteries, we say that when you read the voltage in a battery, you read the differential potential in between this terminal and this terminal. Yes, when you say, oh, my battery is 12.5, oh, it's because the difference, the potential difference in between this terminal and this terminal is 12.5 volts. This is potential difference. It's the difference in between the level of charge in this terminal and the level of charge in the other terminal. Oh, my battery is completely discharged. It's because the potential difference between this terminal and this terminal is zero. This is the meaning of potential difference. And we are going to check which material, which alloy create higher potential difference. Which alloys, in general, we are going to use three types of sacrificial anodes. Sacrificial anodes of aluminum alloys, sacrificial anodes of zinc alloys, and sacrificial anodes of magnesium alloys. Those three alloys, zinc, aluminum, and magnesium, are used like sacrificial anodes. Depending on the water and depending on the material of the hull, some sacrificial anodes create a higher differential potential. The higher differential potential is good because you accelerate the attraction of oxygen on the sacrificial anode and you protect this metal. Depending on the water and the type of material in the hull, the differential potential is better with this anode or is better with the other anode. I have better difference in level of energy in between this and this with this sacrificial anode, or with this or with this. This is the secret. Select the appropriate sacrificial anode according with the water and according with the material of the hull. That's the secret. This is the secret. Select the appropriate sacrificial anode according with those factors. And we are going to check right now what is the meaning of that. Okay, for that reason, in general, the anodes of zinc are eroded, and at the end of the weeks, of the days, the material, the zinc, disappear because will be completely eroded. And of course, the propeller, the rudder will be protected. Of course, in the surface of the propeller, we found a lot of oxide of zinc that the flow of water move it and is accumulated on the surface of the copper. But the copper is not attacked with that oxide of zinc. You can, with a sandpaper, remove those oxide and the propeller will be in good condition easily. Yeah, this is part of the service. Sand the propeller, clean the propeller, remove the oxide of zinc accumulated in the surface of the propeller and restores the propeller with a new paint. Okay, and crevice corrosion. You remember we explained, be careful with the hardware used in your boat. The hardware can attack the boat. No, because my boat is in fiberglass. Yeah, the fiberglass can be corroded because you use regular steel on the bolts, on the hardware. And those regular steels with the salt water, the marine environment, are corroded, and at the end of the day, the fiberglass is completely oxidized and delaminated and destroyed. Yeah, you remember the example in the boat that the stringers were completely destroyed because the people used regular hardware in the motor mounts, and those lac bolts destroyed completely the stringers, and the humidity penetrated the stringers, and the stringers were completely destroyed. The solution was remove the engines. You remember in that process with Mr. Rodriguez, in that process the stringers completely destroyed. We removed the engines, and after that the technician cut the stringers and start the process of reparation of the stringers with a high density foam in the bottom and wood on top. Heavy job. Yes, because the people use improper hardware. Be careful with that. This is the most common problem, the selection of the hardware. Yes, it's basically the problem starts because the people use regular screws, regular bolts, and regular washers, and no marine grade. Remember, the marine grade should be 302, 304 stainless steel, series 18A, 1810, marine grade, okay, appropriated marine grade. And at the end, all of the bolts for crevice corrosion will be destroyed, the threads, and you have a lot of problems when you select improper hardware, improper material. Remember, the galvanized bolts, the galvanized brackets is not authorized in marine steels because galvanized is covered the surface with a coat of zinc, and zinc attract and destroy everything. Okay, be careful with that. All right, and yes, at the end of the day, you have this situation. The fiberglass will be completely corroded. Yes, the fiberglass will be corroded. What is the symptom when the fiberglass is corroded? You can delaminate the fiberglass easily with your hands, and the color of the fiberglass will be like yellow. Yeah, when the fiberglass is completely hollow, it's easy to delaminate the fiberglass, and you need to repair the fiberglass completely. Is possible? Yes, it's possible. This is part of our next course, our course of composite material. We are going to repair the fiberglass. And the stress corrosion, remember, if you bend it the material is broken by stress. Suddenly it's broken because some cracks are propagated with the movement. This is stress, exactly like the stress. Your stress because you work a lot is because you work, never relax, and one day suddenly finito, your heart stopped. Yes, one of the most common elements broken by stress are the shafts, because the shafts are constantly under excessive torque and produce shear load and cut the surface. Yes, it's common that you found the shafts cut, especially in the neighbor in between the propeller and the shaft. In that area is cracked. The crankshaft in diesel engines, when one of the pistons receive salt water. You remember what happened with the piston? The piston expand, block the engine. When that piston is blocked, the rest of the crankshaft try to continue the rotation and is cracked, is fractured in that cylinder. Yes, it's very common in diesel engines because the excessive torque produced for diesel engines. Okay, my friends, for that reason, don't forget use appropriated hardware, marine grade hardware. Only using marine grade approved hardware, you avoid millions of problems and you protect your boat. At the end of the day, it's too expensive repair the boats because you use a regular bolts, regular steel, residential bolts, residential. Be careful with that. No, a friend of mine have a lot of screws. I am going to use those screws in the reparation. No, my friend. Those screws are marine grade? No, okay. Forget that. You destroyed your boat. Use only marine grade screws, marine grade bolts. Use appropriated hardware. Don't forget, it's basically the series 18A and 1810. What is the meaning of 18A? Is 18 of chromium and 8% of nickel. The series are 302, 304, and 316. Yes, in other countries, the 304 is also called the A2 stainless steel. But in the United States, it's 302, 304, 316. The series 18A and 1810. Both of them are good stainless steel. Right? Memorize those numbers because those are the numbers that we are going to use in the future. Those are the appropriated alloys used in marine environments. And now we are going to start with the metallic holes. The metallic holes basically are holes in aluminum or holes in steel. Both holes are commonly used. The most common is aluminum holes in recreational boats, but in heavy boats, in big boats, in mega yachts, is also common steel holes. And yes, you need to protect those holes appropriated, and you need to select appropriated sacrificial anodes per each type of hole. Alright, the aluminum hull. We are going to start with the aluminum hull. You can protect the aluminum hull or with the appropriated paint non-based on copper, free of copper oxides, because the copper oxides are enemies of the aluminum alloys, and at the end of the day, the hull will be corroded. Use a protected bottom paint and be 100% sure that that paint is not based on dissimilar metals, copper or organic material. Be careful with that. Be careful with the copper pennies, I explained before, with the copper washers, because of those pieces of metal in the bilge of your boat destroyed your boat. Be careful with the welding procedure when you repair the aluminum hulls. If you are not a professional welder, I recommend that call professional welders with professional equipment with excellent knowledge in marine materials, because repair the aluminum hull is not easy. Those alloys are special alloys, and those alloys require a lot of experience in the process of welding. Be careful with that. Use professional welders with professional equipment. Yes, especially when the people replace the button. It's possible replace the button completely or repair sections of the button of the boat because it's aluminum. And once again, if you are a good welder, okay. If not, call a good welder. Okay. If you use inappropriate materials, you can accelerate the electrolysis in that area. For that reason, the selection of the welding material for that area is critical. It's very important. Electrical potential. This is the topic that we talked before. Is the difference in energy and why that difference is critical. all the metals generate a negative voltage in comparison to the reference electrode when this metal is immersed in water. In this example, we are going to analyze, I have a propeller in bronze, and we are going to try to protect the propeller with the three different sacrificial anodes. We are going to protect the propeller with zinc, we are going to protect the propeller with aluminum, and we are going to protect the propeller with magnesium. And we are going to try to check which sacrificial anode produce the highest potential difference. For example, with zinc is minus 1.0 volts, and the bronze is minus 0.3. The difference, minus 1.05 minus 0.3 is 0.75 negative. This is with zinc. If I use aluminum, the result is minus 0.8. If I use magnesium, the result is minus 1.3 volts. Of course, with magnesium, I produce a higher potential difference. Nice, interesting. In general, you think that zinc is better. Today, we are going to demonstrate that not always. In some situations, aluminum is better. In other situations, magnesium is better. Okay? We are going to check what happened with the different type of alloys. For example, we are going to check aluminum sacrificial anodes. The most common alloy is the SAMAC. SAMAC is an alloy based on zinc. The technical name is MIL A24779. This is the technical name of the SAMAC. This is the name of this aluminum alloy. The content of this aluminum alloy, this is an aluminum alloy, SAMAC, is the content of zinc is in between 4 and 6.5%. The content of mercury is a little less than 1000. The content of copper is a little less of 4000. Silica is in between 0.08 and 0.2%. Iron is around 0.09%. And the rest is aluminum. This is SAMAC. This is the most common aluminum alloy. It's basically 93% of aluminum, and the rest is zinc with other ingredients. You know that aluminum alloy have a high content of zinc. Zinc is the secret. Okay, but the aluminum appropriated alloy with other metals produce excellent levels of energy, low level of energy. What is the idea? You need to protect the metal with an sacrificial anode with low level of energy. That metal, that sacrificial anode, will be eroded because it's less noble than this one. Can I protect aluminum with a sacrificial anode of an aluminum alloy? Yes, because the marine alloys for sacrificial anodes, they have lower level of energy in comparison with aluminum. For that reason, there are anodes in aluminum alloys used for aluminum boats, because the level of energy of this alloy is too low, and of course this alloy works properly with this in order to protect this hole in aluminum. Yes, there are sacrificial anodes in aluminum alloys good for aluminum boats. Now we are going to check that situation. Okay, SAMAC is an aluminum alloy with a content of around 6.5% of zinc, and the rest is copper, silica, mercury, and iron. Other important alloys are the martyr sacrificial anodes. Martyr. What is the meaning of that? There are two types of martyr alloys. Martyr 1 is the zinc alloys, and martyr 2 are aluminum alloys. Martyr 1 are zinc alloys, and martyr 2 are aluminum alloys. Okay, we are going to check martyr 1 and martyr 2. Okay, martyr 1. Martyr 1, look at this. Is an alloy with a high content of cadmium. You remember in the periodic table that group, zinc, cadmium, and mercury? Those three elements are excellent because they have in the last orbit only 2 electrons. Because they have 2 electrons in the last orbit, the oxygen prefers those elements to attack those elements in comparison with other ones with 3 electrons in the last orbit. Yes, in general, zinc is better because zinc is poison a little, but is not expensive. It's easy to find zinc in comparison with mercury. Mercury is high poison and is expensive and is liquid in natural state. And cadmium is also poison, is too expensive, and cadmium is used in the fabrication of batteries because cadmium is a great storage material of electrons. Okay, for that reason, zinc is used in general for the fabrication of sacrificial anodes. But this alloy, martyr 1, have a good content of cadmium. Have a copper, iron, lead, aluminum, and zinc. And zinc, practically 99.4%. Is practically pure zinc with a little amount of cadmium and other ingredients. This is martyr 1. Look at this. The potential difference for this alloy is 355 amps per hour per pound. What is the meaning of that? This means that a zinc anode will give 1 amp per 355 hours per each pound of zinc. This is an important number, and now we are going to do the comparison with the next one. With martyr 2, martyr 2 is an aluminum alloy, is practically 93% of aluminum with high content of zinc, around 6.5%, and other ingredients like copper, iron, indium. Indium is an other group, other good element located in the group number 3, mercury and silica. But the higher content is aluminum and zinc. This is an aluminum alloy, martyr 2, and this alloy, look at the intensity, is 1225 amps per hour per pound. What is the meaning of that? This anode will give 1 amp per each 1225 hours of every pound of zinc. Yes, in comparison with the previous one is with 355. This is a zinc alloy, is 355 amps per pound. Amps per pound. And this one, this is an aluminum alloy, is 1225 amps per pound. This is better. This is better. What is the meaning of that? The intensity is higher with this aluminum alloy, and the protection is better. The potential difference is higher. When the potential difference is pretty close, that anode is not working because it's the same level of energy. You need an anode with lower level of energy in order to produce a high arc, in order to erode easily the sacrificial anode and protect the metal. This is the secret. Select sacrificial anode with lower level of energy in order to create high potential difference. With this Martyr 2 aluminum alloy, the potential difference is 1225 amps hour per pound. And with this zinc alloy is 355 amps hour per pound. It's less. It's less with the zinc alloy in comparison with this aluminum alloy. For that reason, until this moment, the aluminum alloys are a little better in comparison with the zinc alloys. Okay, aluminum holes. Okay, my friends, don't forget that the bonding is the secret. In general, doesn't matter if the hole is in aluminum, if the hole is in fiberglass, or if the hole is in steel. The bonding is the secret. What is the meaning of bonding? Is connect all the metallic elements inside of the boat to a central piece of metal. This is the bonding metal, and that bonding metal is connected outside with the zinc, and the zinc is basically the ground. That bonding system should be isolated from the structure of the boat. The structure of the boat is not part of the bonding system. The bonding system is separate, especially in aluminum boats. In aluminum boats, you need to be careful. That piece of metal, that bonding metal, should be isolated from the structure. And that bonding conductor should be connected with the external sacrificial anode. Doesn't matter if it's zinc or aluminum or magnesium. The structure should be isolated from the bonding conductor. Okay? And don't forget that table related with the cathodic protection. There are metals more anodics, for example, magnesium, zinc, and aluminum, and chromium, and metals more cathodics, stainless steel, titanium, tin. Those are cathodes, and those are anodes. The anodes are less noble, the cathodes are more noble. The anodes are eroded. It's important that you keep clear this table, because look at the level of energy. See, minus 1600 amps. You remember, amps per hour per pound. And this one, the more cathodic, is only 150 less. Yes, for that reason we are going to try to find an anode, a sacrificial anode, with lower level of energy in order to create a big arc and protect my original metal. Why this one with a minus 1600 have lower in comparison with minus 150? Yes, my friend, because if you have a ruler here and you put 0 over there, okay, this is the positive side and this is the negative side. Okay, minus 150 is here, minus 500 is here, minus 1600 is here. What is less? This is less, is more negative, and this is positive 150, positive 500, positive 1500. This is more, and this is less. Yes. Those elements, the anodes, they have less, minus 1600, minus 1100, minus 900. They have less level of energy. And those cathodic elements, they have higher level of energy. They have minus 150, minus 80, minus 50. They are more nobles. They are more nobles. And those are less nobles. Less nobles magnesium, zinc, aluminum, and more nobles titanium, stainless steel. They are example of less noble and more nobles. In the next coming episode, I am going to explain in details how the water The type of material in the hole and the hardware are important in order to select the appropriate sacrificial anode. This is the next coming episode.